Okay, so today is a short class, and I want to discuss, a systematic formulation of, or start discussing a systematic formulation of perturbation theory. And the reason actually for this is, we'll give it a few more minutes, otherwise we'll open the windows. Yeah, the reason for this is, so far we've taken a rather somewhat simple-minded approach towards perturbation theory, right? We have used the fact that, we've not been careful about how to define the in and out states, and we've not been careful about how to define the vacuum. Right? So, vacuum and how to define in and out states. Right. Now, what do I mean by this, right? So far we've said there's a vacuum, and we've thought about this vacuum as basically the free vacuum. However, we know that this is not quite correct, right? Let's say I denote this as a vacuum of the full theory, okay, which satisfies H on which is annihilated by the full Hamiltonian. Right? And then the vacuum we've been talking about is some vacuum that's annihilated by the free part of the Hamiltonian. Clearly, these two states are not the same. They're not the same because I mean it's H looks like integral pi squared plus del phi squared plus some interaction term, right? For instance, in the lambda phi 4 theory, H looks like this. And H0 just looks like this. And clearly, these two operators are not the same. Not only are they not the same, they don't commute. You see, this operator and this operator don't commute with each other. They don't commute with each other, which is something we discussed earlier as well. H0 doesn't commute with H. They don't commute because there's a pi here. So, it's not, or there's a pi here and this pi doesn't commute with this pi. So it's not the case that, we can just naively work with this kind of a vacuum. Okay. Okay, good.
Okay, so for the free theory, we know that the vacuum is unique, but when you have an interacting mode of
Yeah, we will still assume that the vacuum is unique. We won't assume that the vacuum is degenerate. Why do you say that we can't expect it to hold? You are worried that there might be degeneracies in the vacuum. Yeah. So in general, there are several things one can say about this. It'll turn out that in the interacting theory, provided we add a mass, then the vacuum is expected to be gapped and is expected to be unique. Okay. In some cases where you don't have a mass and you have massless excitations, then there's a continuum of excitations and there might be a degeneracy. But otherwise, in the free theory and in the interacting theory, in both cases, you expect that the vacuum is indeed unique. If the vacuum is not unique, it would have to do with so sometimes there might be what are called zero modes, okay, modes which with operators which commute with the Hamiltonian and don't annihilate the vacuum. That happens in some cases, but not in the kinds of simple theories that we are studying. And the way to see that basically is to realize that is to think of what kind of operators you can write down that will commute with H, right? Because if something is going to transform, if there's going to be a manifold of vacua or some number of vacua, then you have to have operators that go between them that commute with H. And you can check that in these theories you don't have that. Also, by the way, the Hamiltonian is expected to be positive. So it's expected to be bounded below, and we've shifted off whatever constant is required so that this is 0. Yeah. Okay, good. So this is one thing. The second thing is we've not been careful about what we define to be in and out states, right? We've been defining K1, K2. Right? What does this mean really, right? What does it mean to say you have K1, K2? And what we've been saying is, we're thinking of K1, K2 as free part. We've been thinking of these as, so far we've treated these as free states, right? But we know that doesn't make sense, right? Because these free states, after all, are states which are created by acting on the vacuum of on this vacuum with the free field, right? With the and we know that that can't quite be the correct way to think about these states, and we have to think about these states more systematically, and so we need to fix this as well. Okay. Now, so far we were able to get away with this sloppiness, and the reason we were able to get away with this sloppiness is that we were working to lowest order in perturbation theory. And I want to point out that if we work, the moment we start going to one more order in perturbation theory, this sloppiness will come back and hit us. And I want to give you an example of how this will happen. Okay, consider the phi-4 theory. And imagine we are trying to study 2-to-2 scattering in the phi-4 theory. Okay, so far we studied this diagram, right? And we said, well, stuff is pretty useless. So if I study this diagram, and we said, this is minus I lambda, and that's fine, right? However, what if you go to lambda square? What's the next diagram you can write down for 2-to-2 scattering? Any ideas? Yeah, it's a loop diagram, right? And let's say we are still trying to do 2-to-2 scattering. So there are different diagrams you can draw. There's a loop diagram, but there's also this diagram, right? Which is just the diagram where you connect these two legs, okay, and connect this. There are other diagrams you can draw. For instance, there is this diagram. And this diagram we will study later. Okay? But there is, for instance, what right now I want to focus on this diagram. This diagram is really troublesome, because what it's telling us is you get minus I lambda, and then from here you get a minus I lambda. But now notice this momentum is, let's say I call these momentum K1, K2, K3, K4. Now this diagram doesn't depend on these momenta at all. This diagram depends on K1, K2, K3, K4. And what you just have here is, some momentum freely that runs in this loop, and some other momentum freely that runs in this loop. So in fact, the value of this diagram looks like d4p by p squared minus m squared plus I epsilon, just that integral, free integral, and squared, because there are two of these guys. Okay, and that's not a nice result. And in fact, later we'll study the fact there are some divergences that look like they appear with this integral and how you can cancel them off. But this one is a this kind of disconnected diagram. In fact, as we'll see at the end of this lecture and next lecture, is in fact a sign of the fact that we've not been careful about the vacuum and what we are computing. Okay, so you'll get infinities like this. You'll get, and we don't know how to make sense of them, and we'll see this is in fact arising from this kind of a problem. Okay. And we'll get many other problems unless we are careful about how to define what we are talking about. Okay. Okay. So that's the thing the first thing I want to say. Is this point clear that there's something we've not been careful about now that we do need to be careful about? And at tree level, generally, it's okay to be sloppy about this, but it's not okay to be sloppy about this beyond tree level. What is its value? First of all, its value is infinity. You see, because this integral doesn't converge. It's d4p by p square minus m square. Okay. So first of all, it doesn't converge, and so it's infinity squared. Okay. Okay. Is this clear that there's a problem that we need to deal with? Okay. Good. So the road to our systematic study of this starts through a study of correlation functions. Okay, will help us fix these problems. What do I mean by correlation functions? I mean, we think of correlators of this kind in the full vacuum. Okay. Okay, so this is the full vacuum. These are Heisenberg operators. This whole expression is time ordered. It's a time ordered expression. And we are computing the expectation value of this product of time ordered operators in the vacuum. Okay? It turns out that these kinds of objects are very fundamental in many ways. In fact, we discussed them a few lectures some time ago, and they're very important also for other reasons. Okay, for instance, the first thing, which is what is relevant for us, is that we will relate these correlators to the S matrix. But they're just also of intrinsic interest, because this is a general class of observables that you can study in the quantum field theory. Right? We're studying the S matrix, which is one. It'll turn out the S matrix will turn out to be a particular limit of these correlation functions. But there are some. This is also a general class of observables that you can study in quantum field theory. And if you look at formal properties of QFT, often involve these correlators. You see, let's say someone were to say, how do you really define a quantum field theory, right? And the way you really define a quantum field theory, the way mathematicians would try to define it, is by trying to define these kinds of correlation functions. And these kinds of correlation functions, in fact, can also be defined through the Euclidean path integral. And they turn out to be related, to some correlation functions that you can define through the Euclidean path integral. And formal study of QFT often starts by, positing certain properties of these correlators, okay, and then trying to prove that they exist. Okay. Okay. For us, however, in this course, our interest is going to be in this A. Okay. And we are not going to focus on points B and C. Okay. However, today I just want to focus on this correlation function and tell you how you would compute it in perturbation theory. Okay. Okay. So let me write down a formula, and I'll try and prove this formula, and then we stop. Wait, maybe I can write the formula here. Okay, so in this class, we're going to prove the following formula. Okay. This object is equal to, that is all right. Okay. You see, what we have learned to compute so far are correlation functions of interaction picture fields. Okay. So now I'm saying that this correlation function, which is some correlation function of Heisenberg picture operators, you can compute by in fact computing a correlation function of ordinary interaction picture operators, time ordering it, putting in this evolution factor. This is in fact what we have been calling the S matrix, which goes from the, it's the interaction picture evolution from -infinity to infinity of the interacting picture Hamiltonian, computed in the ordinary vacuum, not computed in a different state, but computed in the ordinary vacuum and divided by the ordinary vacuum and the same, the matrix, the vacuum expectation value of this guy. Okay, so this is the formula that we want to prove. Okay, you see, this formula is first of all relating something in the true vacuum to something in the interacting vacuum, is to something in the free vacuum. In fact, if we didn't have a formula of this kind, we'd be in some trouble because we wouldn't quite know how to do perturbation theory. The reason we started with this naive approach to perturbation theory was because we knew how to do perturbation theory if the external states were these free vacuum. Right? So what this is telling us is, what we did so far is not useless. All the Feynman rules and so on we developed are not useless. And in fact, we can compute this quantity, which is a pretty physical quantity. It's a, this is not a quantity that makes any reference to any perturbative split between free and interacting or anything. This is the full interacting vacuum. These are the full Heisenberg picture fields. So this is some intrinsic property in quantum field, intrinsic observable in quantum field theory, not necessarily something that's even perturbative. And we are saying, look, you can compute it in perturbation theory by doing this. Okay, okay, good. So now we want to prove this formula, and this is going to be our objective in the class. Where did I put this thing? You know where I put this thing is? But, here. Okay. I want to prove an intermediate formula, which I realize might cause a little bit of confusion. Okay. It's actually something we should have proved when we did the interaction picture, but let me do it now. Okay. So I want to define this operator. So far we defined the interaction picture. So say we made the split between H equal to H0 plus Hi. Remember, the split between interaction picture and the free, between what you call the free part and the interacting part depends on a time. Do you remember this? What time you make depends on what operator you're calling Hi and H0. That's because the full system is evolving with the full Hamiltonian, right? And so these operators H0 and Hi themselves are functions of time. So imagine we've made this split at some time t0. Okay. Then so far what we've discussed is the interaction picture operator kind of starting from this t0 and going on to some other t. In fact, maybe this has already been clear, but anyway, I want to make it clear. Okay. I want to define this object. Okay. This is an evolution from T1 to T2, not from T0 to T2. Okay. I'm now not trying to evolve from T0 to a different time T, but I'm trying to evolve. I'm looking at this is my definition. I'm looking at this object, okay, and I'm evolving it from T1 to T2. Okay. Okay. So the first thing I want to claim is that this guy is equal to the following object. Okay. It's equal to e to the I H0 T2 minus T0. Okay. E to the I minus I H T2 minus T1 and e to the minus I H0 T1 minus T0. Okay. Okay. How do you know that that this is correct? Well, you check what differential equation this satisfies. Okay. So you can check that if you look at, let me get my eyes correct. If you look at I dui by dt2, then this is in fact the operator that we've considered before, right? Which is e to the I t2 minus t0. This, by the way, I can write as IH t2 minus t0 into e to the minus IH t2 minus t0 into e to the IH t1 minus t0 and e to the IH0 t0 minus t1. So this object that I have, I can write as what we were earlier calling u dagger it2. I can write this as u of t2. This is what we earlier called u of t2, okay, times u dagger of t1. Okay. Earlier we thought of evolution from t0 to t2, okay, and this object that I'm calling u between t2 to t1. So I'm going to make a difference when I write two arguments and when I write one argument. When I write one argument, it's understood that the evolution is from t0 to t2, okay, and so this you can think of as doing the evolution from t0. Sorry, this didn't make any sense. I should have had let 0 here. Yeah. So this you can think of as doing the, this is the operator we have studied earlier. You remember this operator, right? And this is the conjugate, this is the Hermitian conjugate of that operator. When I take the Hermitian conjugate, I get e to the IH t1 minus t0, e to the IH0 t0 minus t1. Okay, you see that? So this I can think of as ui of t2 times ui dagger of t1. Okay. Okay. So this, by the way, I have not proved that this is equal to this. The equality here was that what I wrote here was equal to this. Okay. I have not yet proved that this is equal to this. Okay. But this is not hard to prove, because if you start with the left hand side, then you will find that I is just equal to hi of t2 ui of t2, okay, ui of t2 t1. You see that this must be the differential equation you've satisfied, because remember, I dui of dt2 is just given by this, and this term doesn't depend on t1 at all, right? And so you see that both the left and the right hand side satisfy the same differential equation if you differentiate with respect to t2. Okay. You see this? Okay. What about I dui by dt1? What is that? No guesses? Huh? What should I write? I should write minus? Okay. This is what I should write. No, this is not correct. It's not correct because remember, in time ordering, later appears on the left. Okay. So HIT1 has to go on the right hand side. You can see that from the fact that what you have here is UI dagger. Okay. So when you take the derivative with respect to T1, you will get UI dagger T1 with HIT1 on the right hand side. Okay. So there is a minus sign, but there's not only a minus sign, there is also the fact that the HIT1 goes on the right hand side, which is indeed the differential equation. So this differential equation, this side satisfies and this side satisfies. So they satisfy the same equation in T2, T1. And then you can check initial conditions. For instance, when T2 is equal to T1, you can check that this is equal to 1. Okay. Or when T2 is equal to T0, you can, so you can just check initial conditions. And so, this proves this formula that I have, which we're going to use several times. Okay. Okay. By the way, from here, you can also check that if T3 is a value between T2 and T1, then UI T2 T1, you can think of as UI T2 T3 times UI T3 T1, whereas T2 is greater than T3 is greater than T. Okay. Okay, good. This was just a prelude. Actually, this is something we should have done earlier, but now I'm going to write down, try and prove that formula. Okay. This one. Is this clear to everyone? This maybe it was already clear to you guys, but okay. So now I'm going to assume, without any loss of generality, that x1, 0. Why is this without any loss of generality? Because guys, right now x1, x2 are just labels, right? Within the time ordering, everything commutes. So I'm just going to call the largest time x1, the second largest time x2, and so on. So it's not like there's no assumption here. It's just notation. Okay, so I want to get rid of writing the time ordering every time, and that's why I'm just assuming that whatever the largest time is, I'm going to call that x1. Okay, is that clear? Okay, good. So now let's write down what the expression for this side is, right? The right hand side. So, well, what's the expression for the right hand side? Well, the RHS, which is the RHS above, or numerator of the RHS. First, let's look at the numerator. What does this look like? Well, it looks like 0. Okay. So first we evolve, you see, this evolution goes from, you can think of it as going from minus infinity to xn. Okay. And then the time ordering basically splits up that evolution that you have on top into these different xn's. Right? So you see, what you'll have on the right hand side will be e to the minus I minus infinity to xn hi. We'll get some time ordered guy here. Sorry, let me write Tn, not Xn. Xn is a full time and Tn is T1. So rather than writing 0, I'm just going to call the times T's. Okay. Yeah. Okay. So on. Okay. And in the end, you will get time ordered product from x1 to plus infinity. Okay. Is the structure clear? You see what happened here? The phi's, we already know how they should be ordered. Okay. So what happened here is that the time ordering of this last guy got split up into n different parts. So on the absolute right, you have the times which are smaller than xn. What are those times? Everything from minus infinity to tn. So you get the time ordered product of this guy from minus infinity to tn. In the middle of xn and xn minus 1, you get the time ordered product from from itn to tn minus 1. Right? Then here you will get one more term of the same kind which I have not written. That's what the dot dot dots means, which is tn minus 1 to tn minus 2. Then tn, and so on. And at the end, absolutely, you have x1 to infinity. You see that? Yeah. Okay, good. In terms of the notation that we defined above, right? We can think of this as doing some evolution from, we can think of these are the operators that we've been defining above, right? The operators that we or not above, but the operator we defined in the board that we erased. Okay, the thing that's behind this slide. Okay, so this is ui tn to minus infinity xn. Okay, and you have ui tn minus 1 to tn phi I xn minus 1. You have ui tn minus 2 to tn minus 1, okay, and so on. Okay, and then you have phi I x1, and you have ui plus infinity to x1. Okay, Okay, good. Now these time evolutions that you have, you can use the formula that we had before, okay, to convert them into something which evolves you from t0 to tn. Okay, so this guy, for instance, you can write as ui using the formula that we had before, tn minus 1 to t0, okay, into ui dag, or let me just write ui with one argument. You could write this as ui of tn minus 1, okay, into a ui dagger of tn. Do you see? This you can write as, so what do we have here? This you can write as a ui of tn, okay, and then a further evolution from t0 to t minus infinity. Okay. So what we have here is phi I xn. Then we have ui of tn minus 1. We have phi I of xn minus 1. The same thing I can do to this guy. So this becomes ui dagger of tn minus 1. Remember, by single coordinate, by single argument, I mean the other argument is understood to be t0. And then so on. Similarly, for phi I x1, I have ui of x1. I have ui dagger of x1. And then I have evolution, again, the conjugate of that is infinity to t0. Okay. Is this formula clear? Okay. You see, what have I done? I have here evolution from minus infinity to tn and evolution from tn to tn minus 1. I wrote this as evolving back in time to t0 and then evolving forward in time to tn minus 1. So this is, I wrote as evolving from tn to t0 back in time and then evolving forward from t0 to tn minus 1 forward in time. That's why I got a u dagger here. This is evolution from minus infinity to t1, which I can think of as evolution from minus infinity to t0 and then evolving, from t0 to tn. Then I evolve back in time. Then here I have evolution forward in time, then evolution backward in time, then evolution forward in time, backward in time, and so on. Okay, do you see, is this clear to everyone? If it's not, if you write it out, it'll be clear to you. What are these quantities? Do you recognize this? These are the Heisenberg operators, right? So we see we are already starting to get the form that we want. Okay? We have some additional factors, but we'll deal with them in a second. Okay. This is now phi Heisenberg of xn, phi Heisenberg of xn minus 1. And then I have this ui infinity to t0. Okay. So the numerator I've converted to this form. There was a time ordering here. This is actually correctly time ordered. This is time ordered. Except I have these factors on the right hand side, but otherwise you see that the Heisenberg operators that I have above have started to appear. Okay. Okay. Is this clear? Let me see if I wanted to say something else. Okay, good. So now let's look at this factor, right? Which is ui from t0 to minus infinity on 0. Okay, let me make a box here. You see, this guy, this is what we were, if you go back to the formula we wrote previously, one of the factors that we have is just, is t0. Okay. So this you can check looks like e to the minus I h into t0 plus infinity. Okay. Actually, most seriously speaking, I should take this to be some capital T and take the limit as capital T goes to infinity, but please excuse me for writing t0 plus infinity. This by itself is not a sensible thing. Really, it's the limit that we want to talk about. Okay, but I'm going to be a little sloppy with my notation. And then we have e to the minus I at 0 into minus infinity minus t0. Okay. This came from, what you had here was t0 minus the time, and minus of that time became plus infinity. And what you had here was, the time that you had on the right hand side, t2 minus t0. Okay. So this is what you get. We want to act with this on the free vacuum. But the free vacuum by definition is the part which is annihilated by h0. So this factor doesn't contribute anything, even if you evolve the free vacuum with the free Hamiltonian for an infinite amount of time, you don't get anything. Okay. So this is just e to the minus I h into t0 plus infinity, whatever that means, on 0. Okay. Now we have to make sense of what this quantity is. Okay. Good. Now what is this quantity? This is the full Hamiltonian acting on 0, but you're taking a state and you're evolving it for an infinite amount of time with the full interacting Hamiltonian. Okay. What happens when we do this? Well, this state 0 that we have is not the vacuum of the full Hamiltonian, right? However, it has some terms. So we can write 0 as some amount, some c times the vacuum, okay, plus these are energy eigenstates, right? Okay. Now, what happens when we evaluate with this e to the minus I h when we evolve with this term, right? This term stays what it is. You get this factor c, it is what it is. Okay. And then you get here plus cn into e to the I en into this e0 plus infinity on en. Okay. Now, what is special about this is because this coordinate is infinity, these are things which are oscillating a lot for any value of en. Okay. In particular, if you take some other state, which has some other spectrum, right, which looks like, what should we call it, km en plus k in the vacuum. Okay. And if you look at the matrix element of these guys, if you look at psi then this just comes out, this factor just gives you what it's going to give you. This looks like kc, okay, which came from here. Okay. But then the other terms that you get look like plus, okay, some sum, okay, of kn cn e to the minus I en into t0 plus infinity. And what this means is, remember that in quantum field theory, the spectrum of energy eigenstates is always continuous. Okay. So if you start with some smooth distribution of kns, what you get here is some distribution of kns weighted with some crazy phases. Right? So you get the same kns, but now they're weighted with some rapidly oscillating phases. And when that happens, if you start with any reasonably smooth distribution, you can check that this kind of sum is always 0. So these phases you can ignore, and what that tells you is that these rapidly oscillating terms do not contribute matrix elements. Okay. There's some assumption here, right? The assumption that we're making here is that we have to look at states, we have to look at matrix elements between this state and some other states that are slightly smeared in energy, okay, that have some smooth distribution of energy eigenstates. And this is the kind of assumption that you often make in quantum field theory, where you always consider matrix elements, or you always consider functions which are, and you are always allowed to smear them a little bit. So you always want to consider matrix elements as distributions, not really, what happens if you take a particular state, then this might or might not be zero. If you take Kn to be, literally one eigenstate, then this won't be zero. It will be just some crazy phase. But if you take it to be some smooth superposition over eigenstates, then you'll see that, you'll get these phases will cancel. Okay. That's why this term goes away. And what you get here is this. Therefore, for all effects and purposes, this guy, this evolution effectively just projects onto the vacuum. Okay. So this evolution is effectively like the vacuum into this term here, which is the vacuum in the inner product 0. Okay. Okay. On the other side of this expression, we have another evolution which now looks like T0 to plus infinity acting on 0. Okay. But we know how to deal with this, right? So this effectively looks like the vacuum times this. And we see by the same argument, this also projects onto the vacuum and gives you another factor. Yes, that's right. Well, yeah, so that's an assumption that you make in perturbation theory, that the true vacuum and this interact and this vacuum always have some overlap. As long as there's some overlap, it'll work. Okay. So this is equal to 0 times omega, and then this is gone. This factor is gone. Right? And now you have here also omega times 0. Right? Okay, but this is great, right? Because what do we have here? We have 0 times omega times 0. So this is just the mod square of 0 times omega. Okay. And now we've got back this. In fact, I had not written the time ordering because of that assumption, but of course I can put back the time ordering for free just to make it look a little bit more like this formula. Right? Because this is time ordered. X1 was larger than Xn, but I can put back the time ordering. Okay, good. Now what about the denominator of the formula? Well, the denominator is pretty simple because the denominator is just evolution from minus infinity to T0 and evolution from T0 to infinity. So it's just the product of these two factors with no phi's inserted. You see that? So that's what we had to say about the numerator. Well, the denominator, if you like, you just do the same calculation, but don't insert any phi's. You see that? Okay, these factors just cancel. And therefore, we have shown that this is equal to that. Okay. Okay, this is an important formula. It's a pretty useful formula for us. It will kind of guide how we do perturbation theory. So you should understand this well. And some of the manipulations here are important, but you should understand this formula well. Okay, are there any questions about this? Well, there's some assumption that's required. Sure, I mean it will be true. Even if the overlap is very small, it will cancel between the numerator and the denominator. But yeah. Okay. Uh, well, okay. In fact, since I have to go in 5 minutes, I'm not. Let me not say something more. I wanted to show you how. I'll show you at the beginning of next lecture. How, in fact, this disconnected graphs that we found at the beginning will cancel completely if you use, once you are careful about this kind of a formula. And how, in fact, the Feynman rules for this basically tell you just to sum over connected graphs and not to sum over disconnected graphs once you correctly take into account this quantity. Okay. I want to also note that, these kinds of quantities that we have on the right hand side, we in fact know how to compute them in perturbation theory. How do you compute them in perturbation theory? Well, you just expand out that time ordered product and use Wick's theorem, right? Because everything on the right hand side is given in terms of interaction picture fields, right? So you expand out that to as many orders as you like, and then you just use Wick's theorem, right? And we know how to use Wick's theorem, right? And you just do contractions. So, for instance, let me give you an example. Okay, let me give you one example and then we'll stop. Say I want to compute the 4-point function in phi to the 4th theory. Okay. Say we want to compute and say when we in the next class we'll see how if you go to next order in lambda, okay, this disconnected diagram that we have will go away. But first, let's just consider the first order term in lambda. Okay, how do you compute this first order term in lambda? Well, you just expand this out to first order in lambda. So in fact, the denominator doesn't have any contribution at order 1. Order 1, you just get 1. Okay. So you'll just get phi I x4, and then you'll get this guy, which is hi x. Okay. So now you can do various Wick contractions. Okay. And what answer is this going to give you? What is the same that we got? Huh? Okay. Huh? Okay. And then? There are 8 phi's. Yeah. Good. You see, the point is that how do you think of this? It's still Feynman diagrams. However, it's true there are 8 phi's, but all of them are going to contract pairwise, right? And there's a 4 factorial that went in, and that 4 factorial you will still get. However, the only difference is that between these external points and this point, you'll get propagators. So you'll get g of x1 x. This is x1. G of x2 x, but this is the propagator. It is the time ordered propagator. G of x3 x. G of x4 x. Okay. And you have this integral over d4x. So this is the answer that you get. In momentum space, what will this look like? If you Fourier transform this, you have an integral, it will just become the product. This will just look like minus I lambda, I by k1 squared minus m squared into I by k2 squared minus m squared. K1 is conjugate to x1, k2 is conjugate to x2, and so on, obviously, right? There's k3 and then k4 squared. Okay. So the Feynman rules for computing these kinds of Green's functions are very similar to the Feynman rules we've used for computing what we were thinking of as S matrix elements, except that you have to keep also the external propagators. You see why you have to keep the external propagators? This is an example that shows. Okay. So it's the same as what we were computing so far without calling it that was kind of amputated Green's functions. So we were not keeping the external propagators. We were thinking of them as contracting with some external legs. But when you compute these kinds of Green's functions, you're supposed to keep the external propagators. And in fact, the LSZ formula that we'll study in some time will tell us in a precise way that S matrix elements are given by stripping off these external propagators from Green's functions, which is how we were kind of already intuitively doing things. But it'll give this formula to us in a more careful way. Yeah. Okay, good. So let me stop here, and next time I'll tell you why these disconnected diagrams cancel. Are there any questions about this? Okay. So this was a short lecture, but even then, this formula is an important one to know, and you should all be clear about it. Okay, so I'll stop here.